All right, section 6.4 is the calculus of specifically the ln of x. We're not going to play around with bases other than base e, which we know is ln x. So the function of interest y equals ln x. So the question that we're asking is, what is the derivative of this function? Well, if y is ln of x, by definition of a logarithm, base e to the y is equal to x, right? And this is a logarithmic representation. This is an exponential representation. So what I'm going to do is take derivatives of each side with respect to x. So I'll have the derivative e to the y is e to the y. Remember your implicit differentiation. When you take the derivative of a y term, you introduce y prime. And the derivative of x is, of course, 1. So if I solve this for my derivative, I have this thing. Well, it's not very appealing, but I can see here e to the y is equal to x. So y prime is 1 over x. Okay, so our new differentiation rule, derivative of ln x is 1 over x. Okay, so that's our vanilla rule. That's the derivative of one function. Not real useful. It is useful, I shouldn't say that, but we're more interested in the ln of anything, right? Where u is an expression or function in x, conglomeration of x. And again, the pattern is the same as always with the chain rule. Right? The derivative here will be 1 over u, and you attach the u prime. So I'm going to write that u prime on top. So this is the rule that you should have on your list. Okay, so one thing I'll point out is, you recall, the derivative of an exponential contains an exponential. When you take the derivative of the natural log, there's no ln over here, right? So it's u prime over u, right? The derivative of this argument over the argument itself. And again, this is useful because this gives us our antiderivative rule. Note that this is absolute x. That's because that is the most general antiderivative for this thing. So, and also point this out, these are the same, right? But mathematicians are lazy, so they'll typically write something like that. Okay, so you have a derivative rule. They summarize. I know I made a little bit of a mess over here. These are the rules that are in play. Derivative of ln of something. Okay, that's my, and okay, so add those to your list. All right, let's see these in action. So we'll do some derivatives. It's actually a relatively easy rule to work with, I think. Although everything's easy if you know how to do it, right? Let's start out with maybe a nice light one. So we're going to differentiate. Let's see some examples here. All right, let's try y equals 1 over ln of x. So I'll do this maybe two ways. Right? I'll use a quotient rule here. Remember the layers. Remember the onion, right? The first layer of this onion is my quotient rule. Within that, I see the rule that I just wrote down, right? Derivative ln. So I have the bottom, derivative of the top, which is 0, minus the top, derivative of the bottom, which is just ln of x. I know that's 1 over x. I'm satisfied with that. Bottom squared. So this zeroes out, right? So what do we have here? Negative 1 over x. Okay. Also, just want to point out, this is coming over here. Right? If you have a constant on top, sometimes you can pull this trick. Nobody likes the quotient rule, right? So if I do this, now the first rule, the first layer of this onion is the chain rule, my power chain rule. All right, so if I bring this down, subtract, right, derivative of the inside, 1 over x. Okay, one thing I think I mentioned this before, we don't want these, right? We don't want to leave those in our final. So I want to make that positive by pushing it down, and let's make it down here. Okay, so of course they're the same. That's a nice easy one. Let's try this one, differentiate. Mix up the letters here. Square root 1 plus, this one shouldn't be too bad either. 1 plus ln(t), right? The hat is very little use. So something numerical, that's a 2, believe it or not. All right, so again, this is a lot like the last one, a lot like the second solution. This is chain rule, power rule. Let's bring the half out. Subtract 1. What's the derivative of this inside? Same as the last one. The 1 goes away. I have 1 over t. Okay, so we have this. We have a little cleanup duty. We'll get the things in the denominator that should be there. And I'm going to go back to the hat. I'm going to go back to the root. Okay. So that's no big deal. Let me see. How about something like this? Differentiate. So you got a nested functions here. So this is tangent of something. So the first layer of this onion is tan, right? My tangent rule. So I have tan u. So this will be secant squared of said u, derivative of the inside here, 1 over x. I can just pop that on the bottom. That's a one-liner. Almost too easy. How about all right, so this one is incorporates the real one, right? Got to get used to using this. So this is ln of something. So this is the layer, first layer of this onion. So again, if I can read and write, I can just copy this u. That's not a problem, but I need the u prime. So that'll be a product rule. So that's kind of the second layer of this onion. So I have first, derivative second, plus second, derivative first. And there's a nice simplification hiding here. That's not hiding, right? Look all right. Yeah. Seemed too nice, too clean. All right, good. Let's maybe see one more. One more derivative, excuse me. How about, let's pick one that looks like fun here. Now, differentiate. Square root. All right, so again, let's do this. This is it's like that. So the first rule in play here is my power chain rule. One good habit is make sure you have this notation accurate, right? What I did is I rewrote y. Sometimes students will have a tendency to put a y prime here, but you haven't differentiated yet. So don't use y prime until you're actually taking a derivative. Power rule, right? So now I need derivative of the inside. I ran out of room. Son of a gun. So I have cosine x plus, and now I have the derivative of this guy. That'll be my ln rule. So I'll have cosine, right? That's u prime, if this is my u. Cosine over sine, that's cotangent. So again, I'm going to move this negative exponent into the denominator with the 2. That looks okay. And then up here I have this. And I'm going to switch that over to cotangent. Okay, how's that? All right, it's kind of a mess. Let's see some antiderivatives. Integration. Right, I'm just going to pop this rule here, just from memory, right? Let's try this one. See what this looks like. Integrate. So this will be cosine Okay, again, think of the thought process. There's no simple formula to do this one, obviously. So we're thinking U substitution. That's our technique. So if I let U be ln of t, du is 1 over t dt, right? So I can write cosine of u. So this is taken care of. And now I have 1 over t dt remaining to substitute out. That's simply equal to du. Okay, so this will be sine u plus c sine ln t plus c. Okay? Integrate. Okay. You're probably going to see a similar pattern here for many of these problems. Let's make this the bottom. So then du will be cosine x dx. So this, this is real clean. The bottom here is u, and then cosine x dx is du, and then if I see what I have here, this is the rule that I just had on the last page, right? This is this. These guys are the same. It's just a different letter. So this will be ln u plus c, which is, of course, back substitute. Okay? What else we got here? Let me take a look. Let me look at my... All right. Let's see another one here. E to the x. Okay, so you look at this. Right? Don't be tempted to break this in two. You can't break up denominators. You can always break up numerators, never denominators. Maybe we could do this with a u sub. 1 plus e to the x. Right, derivative, that goes away. This is e to the x dx. So this mirrors the one above. That's why I did them on the same page. This is simply du over u again. Right? I have my u on the bottom, du on top. Same problem, really. Back substitute. Okay? Oop, there we go. So, The last thing in the section is a technique. This is a technique for differentiation. And I'm going to put down, it's a little simple, let's write it down. It's called logarithmic differentiation. This is not a new formula. This is a technique. It's quite a mouthful, huh? And I'm going to put the recipe here. It's quite simple. The recipe is not necessarily the problems. I'm going to do one right here. Let me pick it out of the book. Where are you? Okay, here we go. Oh, yeah, we're good. We're good. Let's see. X squared, square root, x squared plus 1, 3x plus 2 to the 5. Hopefully you can read that. Okay, we want to take a derivative of this thing. So let's think about how you would do this as of today, as of this moment. You would start, when you think about the layers, you'd start with a quotient. Then when I got to take the derivative of the top, there's a product in there and even a chain rule with this root. Take the derivative of the bottom, there's a chain rule. I would fill up 2 pages doing this. Probably make 2 mistakes. So this is a technique that you can use when sometimes you have these things that are a mess. Sometimes, and it doesn't happen too often. If somebody asks you to take the derivative of that, you'd probably tell them to get lost. But sometimes this technique will make your life easier. So step 1 is we're going to take the natural log of each side. Okay, so this will be ln of y, and this will be ln of this monstrosity. Actually, the one in the book is even nastier, but I didn't want to run out of room. Okay, so why did we do that? Well, if I look at this thing, this is a log now. Think about those 3 properties of logs where you can take something like this and you can split it up. You can split up a quotient with subtraction. You can split up via addition, etc. So let's see what that might look like. I'm going to kind of move this over here because I'm going to need room. So I'm going to write step 2 down. Use properties of logs, specifically the ln here. So let me put it here just in case. I don't want to run off the table. Okay, I can split up a quotient. We just talked about that. And I'm going to do 2 things at once just because I have limited space here. I'm going to split up the quotient via substitution, or subtraction, excuse me, and split the product. This is, and then minus that thing, right? Okay, that's pretty good. I can even take it a step further. These exponents, and I should, these exponents I'm going to pull out. This one too, I didn't even see that. My bad. Sorry, that's pulling that 2 out. Now you might be saying, so I'm using the 3 basic properties of logs. So you might be thinking, well, you turned one mess into just another mess, and I couldn't argue with that. But the derivatives here are simple, right? They're really quick and easy. So I'm going to differentiate, keeping in mind this will always be the same. On the left is an implicit differentiation. All right, so the derivative of ln of y would be 1 over y, but then you pop out the y prime. Right, so the left-hand side of this looks the same every single time. And so I'm going to do that, and I'm going to do it on the next page. Okay, so let's do it like this. I'll try not to do this too much. All right, derivative of the left here, right? 1 over y prime via implicit differentiation. All right, 2, 1 over x. Okay, what about this thing? 1/2, right? This is ln of u, so the derivative will be u prime over u, right? So this is 2x, 2x over 2x squared plus 1. And this will be, again, the same situation. I got a 5. Derivative u prime here is 3. 5 times 3. All right, and I should, of course, cancel these 2's. So this is pretty good, but at the end, we don't want this on the left. Solve for y prime. And that's the same every time because this is the same every time. So the y goes up. And of course, this guy can't stay, right? So what I need to do is put this ridiculous thing, which is y, substitute it in for here, okay? So if you want to see that, I'm sure you do, just to see what a final answer would look like, this ridiculous thing here. And then, oh, this mess. I just think what this thing, well, and I mean, you could argue how much work I saved. You know, maybe it didn't save a lot of work. Point being, for this example, this technique was a matter of choice. Convenience, that could be argued. All right, I just had to grab a quick sip of water there. All right, so the next example is a little bit different. Say I need to take a derivative, maybe of this thing. Let's make x to the tangent of x. So this is a very easy mistake to make. This is not what it is. Not equal to. You don't bring this down and subtract 1. Why not? Well, the power rule is x to the n, where this is a number. This contains a variable. So you see students make this mistake a lot. If a variable is in the exponent, the power rule does not apply. And in fact, that variable needs to come out of there and it's trapped. So in a case like this, the logarithmic differentiation technique is a necessity. That is the only way to do this problem. Any other of this nonsense will crash. And it takes advantage of the property of the exponent inside the log. All right, so if I take ln's of each side, I can use that rule. This is an exponent, I can pull it out. Okay, that looks pretty nice. So again, the left side of this is the same every time. This is now a simple product rule. First derivative second, second derivative first. And again, the ending's the same. I'm going to bring that y up, and I'm going to do it in one step. I'm going to bring that y up, and I'm going to substitute it back in. So I want you to note the difference between the two examples. In the first one, it was a choice. Whether you thought it had improved, the workload or whatever, that's debatable. But here, there is no choice. The variable in the exponent leaves you no choice. You have to get it out of there, and this is how you get it out of there. You have a log, you can pull it out. Okay? So, sort of mechanical stuff. I know that when you just have derivatives and antiderivatives, it's a little dry, but I try to give you some examples. There's examples in the text. I wanted to point this out. I might add this to my email, but I'm just going to say it. There, for 6.3 and 6.4, there are two different sections. One of them, there's two of them, but one set of two is white, the other set of two is blue. We are doing the white, okay? So that's important. They're pretty much the same, but the exercises are different. So if you're doing them out of the blue one, you're doing the wrong ones. I'll put that in the email. Have a great day. Have a great weekend.